it's useful to know who the audience is, and it indicates to me what I need to speed through and what I must slow down on. I think there's a lot of speeding that I need to do. My focus is on the Mine Waste Directive, the requirements of the Mine Waste Directive, and the corresponding best available technology guidance. And I'm also going to look at international guidelines from OECD countries, particularly from Canada and Australia, the things that they emphasize, which are not emphasized as strongly in the European guidelines. So the legislation and guidelines on mine waste management has been developed in response to disasters. And on the slide, I'm just quickly showing some of the key ones that have influenced legislation. More recently, Samarco, that's Abafan there, which is quite a while ago, and that's Atnacoya in Spain, which together with the Baia-Marie disaster in Romania, which I'm not pronouncing correctly, but those two influenced the Mine Waste Directive. That's Samarco again. I couldn't get a nice picture of Mount Polly in Canada, which is another recent disaster strongly influencing legislation. And then there's Merrispate in South Africa that has had quite a profound influence on international legislation. The Mine Waste Directive, it has to be transposed into the legislation of every EU member state, and it's transposed in every country differently. Sometimes it's in the mining legislation, sometimes it's in the planning legislation, sometimes it's in environmental permitting legislation. But in most countries and provinces, it's identical. It is what is in the Mine Waste Directive. What is interesting is that it is interpreted differently in different countries. The European Commission conducted a study, or had consultants undertake a study in 2017, or 2016, 2017, and they found that the directive was interpreted very differently across Europe. And they are talking about producing guidelines that will improve the interpretation of the directive. Anyway, the overall purpose of that directive and the corresponding legislation is to prevent pollution and manage the stability of mine waste disposal facilities. And it requires that mines produce a mine waste management plan, and that's approved by the government. What's good about the Mine Waste Directive is it's sensible legislation for mine waste, and it exempts mine waste from other waste legislation in Europe. It applies to those wastes listed on the slide if they're at the mine site, and it also applies to the mine waste water holding facilities. So any water that has come in contact with mine waste has to be included in the mine waste management plan. A very important point to make, and this is, there are a lot of new projects being planned in Europe, and I saw a project quite recently where they were looking at moving the concentrator 20 kilometers from the mine site because of landowner issues. But the problem is with that is that the concentrator is no longer at a mine site and the waste is no longer mine waste, so it's subject to different legislation. It can't be slurried, and it's subject to very high landfill taxes. In most European countries, wastes other than mine waste are subject to very, very high landfill tax. In the UK, landfill taxes are about £86 per tonne. Can you imagine spending £86 per tonne on your tailings? And I understand, well, I know in other European countries the costs are that higher as well. So that is quite important to take into account in planning. It can influence the alternatives that are chosen. This is just what has to be delivered in a mine waste management plan in a nutshell under the Mine Waste Directive. I don't want to labour on it. It's very simple, actually. It's necessary to provide information on each waste stream. waste characterization is hugely important because it influences what you can do with the waste. Mel is going to talk about the geochemical characterization of the waste. So if you want to put backfill into mine workings, you've got to pay attention to that geochemical characterization of the waste. And it needs to be done very, very early in the mine planning. You can't go through your pre-feasibility study and feasibility study thinking you can put all your backfill in the workings and then discover that the waste classification is such and its potential impacts on groundwater are such that you can't place the backfill in the workings. And the management measures that have to go into the plan are fairly straightforward for a tailings dam engineer. There needs to be a high emphasis on stability and pollution. There's a very strong link between the Mine Waste Directive and the Water Framework Directive. It's also necessary to produce a closure plan for the mine waste facilities and the water holding facilities, and often that ends up being a plan for the whole site anyway. The regulatory authorities can't approve that plan without making sure that there is some form of financial provision for closure. If the facilities are Category A facilities, there are some additional measures required. Category A facilities are facilities that regulatory authorities are going to pay much more attention to. They're facilities that could fail. There could be a major accident if they fail, and facilities if any waste is classified as hazardous. And not much more is required for a Category A facility as for any other mine waste facility. Just a major accident prevention policy, a proper safety management system, and a proper emergency plan. The emergency plan is quite important. It requires extra work. Emergency scenarios need to be developed and understood and proper controls put in place. And then the regulatory authorities have to produce an external emergency plan. The corresponding reference document that goes with the Mine Waste Directive and its legislation, the BAT, Best Available Technology document, or BREF document, produced in 2009. It's a huge 600-page document, and it's full of examples on best practice. It's actually not prescriptive at all. It makes the point that what's best for a mine in each mine is unique to each mine in its unique setting with its unique wastes. And that's why you have the site-specific plan that is approved by the regulatory authorities. The thing that the BAT guidance emphasizes that is not strongly in the legislation is highlighted in orange. It says that the BAT must be supported with site selection documentation, with a risk assessment, and a water balance and management plan. Now, the water balance is really important. The Australian and Canadian guidelines make a very big thing about water balance, which I'll talk more about later. I'm not going to talk about these subjects at all. These are the topics that have to be covered when developing the mine waste management plan, the topics you have to think about. As I said, the BAT guidance is not specific. It just lists a number of topics that have to be covered. There is a prescription on raising dams. They discourage the use of upstream dams in seismic regions. The other things just have to be considered. There is a prescription on cyanide management. The directive and the BAT guidance are much stricter than the cyanide code. The 5 times lower levels of cyanide have to be, the levels of cyanide on the tailings dam have to be 5 times lower than what is allowed under the cyanide code. So the cyanide code allows 50 ppm wad cyanide. Under the Mine Waste Directive and the BAT guidance, it's 10 ppm wad cyanide. And then the other items highlighted in orange, we're going to be talking about those a little bit more. Other international guidelines make quite a big thing of those subjects. The recognized international guidelines, mine waste engineers recognize the Canadian guidelines as very good guidelines. Their guide to management of tailings facility was updated in 2017, and they also have a guide for operation, maintenance and surveillance of tailings facilities, which most tailings dams engineers use. I'm sure you agree with that. There's also Australian Leading Practice Guideline 2016, which is meant to be an international document. And in Australia, it is also used with local legislation. And those guidelines do recognize the European legislation, but they do recognize it as a little bit out of date, having been developed in 2006, the back guidance in 2009. And they even recognize the South African guidelines, which are quite old. Then tailings dams engineers also use this technical guidance listed on the side, the ANCOLD, the ICOLD, and the Canadian Dam Safety Guidance in the design of facilities. But that care must be taken in using those technical standards, because often the legislation of European countries is even stricter. That's the case in the UK. The dam safety legislation is even more strict than these international guides. The Canadian guidelines also refer to the ISO 14001 management system standards and use that as a base for management systems. So all of the above guidelines and standards need to be used with applicable legislation, which might be stricter in certain jurisdictions. I also mentioned this book, which has come out very recently, 2018. It isn't an officially recognized guide, but it's a very useful interpretation of the European legislation and guidance. It's edited by Mike Cambridge, who is very frequently involved in the review and approval of mine waste facilities around Europe, especially tailings dams. It does, however, focus on hydraulic transport of tailings, so slurried tailings. It doesn't deal with dry stack facilities. So the trend that we're seeing internationally and is encouraged in the objectives of the Mine Waste Directive is minimization of waste. And we're seeing the modern mines that are being developed in Europe, planned, they haven't been approved yet. They are definitely being designed reducing the waste from the workings, so they are trying to keep as much waste rock underground as possible. And designing the workings so that backfill can come into the workings as much as possible, and then also using waste in construction when they can. Then processing operations are becoming a bit more complicated. There is the aspiration to recover other valuable minerals. I haven't seen that, but I have seen some process flow sheets that produce byproducts such as sand and mica. So they've got extra flotation steps in processing, pulling off sand and mica as byproducts and reducing the concentration of the volume of waste that has to be disposed of. Also flow sheets where there's a flotation step to reduce the amount of materials subject to a chemical such as cyanide. So you'll have a flotation step taking about most of the mass pull of the plant out of the plant, and then quantity of material exposed to cyanide reduced 10 times. And then processing, adding on processes to treat waste, such as cyanide treatment processes. With waste storage, there is lots of mines are being planned with backfill. Everybody's thinking about backfill, trying to get it into the workings. There's some countries that consider the backfill to be a product once it goes into the workings, no longer a waste. You still have to prove it's not going to pollute groundwater. There is a very strong trend towards dewatering of tailings on the projects that we see. And everybody's thinking about that because it reduces liability. Lining and capping of tailings dam is not required under any of the international guidelines. It's not required in the European thing. It's something you have to think for, but it's not a prescription. But we see regulatory authorities demanding that increasingly as an extra precaution, and sometimes it is essential to prevent water pollution. And obviously revegetation and more active water treatment. Now, just moving on to other guidelines, the International Council of Mining and Metals, after the Mount Polly and Samarco disasters, undertook a huge big review of tailings dam management practices around the world, and they came to the conclusion it's not the design of the facilities that is a problem anymore. It is the governance and the assurance that needs attention. And the Mining Association of Canada updated their guidelines. They put all their guidance in the form of a management system. Sorry, the slide is not terribly clear. We've actually got a neat summary of that management system if you would like to email us, and we'll send it to you. They have added in emphasis on a risk-based approach, saying that the risk assessment must look at the risk of failures, they must look at the geochemistry, must look at the water management, they must look at the placement of tailings in mined out areas. So there's the answer, that it's absolutely essential in every mine planning exercise to think about placement of tailings in mined out areas. So it's highly encouraged. And they also emphasize the need for critical controls to manage high consequence risks. Another important thing is the engineer on record. So there should be an engineer on record on a site responsible for a tailings facility from design through construction, through operation, all the way to closure, and the importance of independent technical review of the facilities. The Australian leading practice tailings management guidelines said the most recent incidents can be attributed to lack of control of the water balance, causing overtopping, inadequate adherence to design, poor construction control, and tailings deposition and decant management not being undertaken in accordance with the intent of the design. They've got some basics for tailings management, and I'm not going to elaborate on that, except they make the point that all available storage methods should be considered, and they say there is a very strong trend towards dewatering in Australia, and that must be considered, and damming of surplus water on the tailings storage facilities must be elimination of that damming should be considered. They also emphasize regular review by appropriately qualified engineers. And the one thing that the Australian guidelines make a big point about that no other guidelines make about, and that's about the closure objectives and completion criteria. And I'm just going to switch to what they predict for the future. They say in the future there's going to be management system upgrades and much more effective monitoring of tailings dams, managing of change, and peer review of tailings facilities. And they also predict in future there will be a reduction in slurry tailings transport. Just end with this slide before Jamie can talk more about this. But as I've said in this talk, we do see a trend towards dewatering of tailings. It is more expensive, but in many circumstances it is attractive because of the way it reduces liabilities.
Yeah, Jane, just to jump in on that point, I think it really relates back to some of the questions that have come up from Tony and Nikolai from Buchan. I mean, the in-pit, it's interesting you both bring up the pit disposal, in-pit disposal, and the key thing there is management of excess water, and if you can look at a kind of overall process optimization, so look at recovery of water in the plant by dewatering, you send less water out to your facility and therefore you have less to manage when it goes into the pit. And the key things about in-pit disposal are making sure you achieve a suitable density for storage of the tailings in there, but also minimising seepage to the environment. And how do you line these big open pit structures? It may be very costly, and there are ways to do that, which we've done before, but you can offset some of those costs at the disposal facility by dewatering in the plant, because you can recover water and it will save bringing in fresh water from another location. In Australia, where Tony's got a lot of experience, that is on every operation. you need to look at dewatering purely as a cost-saving measure. It's got the added benefit of obviously reducing geotechnical risk, and as a geotechnical engineer, that's always what I'm going to focus on. But you have to look at it as a kind of whole life cycle thing. You can't just look at the cost of putting tailings in the pit, maybe dewatering them to a filtered tailings or a dry stack material. It's going to cost a lot of money to do that, but look at the cost savings you've got in the plant and try and integrate that in there. Yeah, it's just this graph really, it's by Davis, who is a famous tailings practitioner. It really highlights this increasing cost to dewater tailings, but the significant reduction in geotechnical risk. But we've got to look at cost-effective ways to do that and be smarter about how we do that in this current kind of climate where huge quantities of tailings are being produced as we get lower grade ores and we're processing them. So, yeah. So, anyway.
Hi, okay, I'd just like to give a brief overview on geochemical waste characterization and basically the importance of this, just a high-level introduction and the importance in terms of both the legislation and managing the risks to your project, and hopefully convey the importance of doing the characterization early on in your design stage. So the way I'll handle the presentation is basically, first of all, cover off the most likely geochemical risks associated with mine waste, why the waste characterization is actually needed, how it is normally done, and what influence that has on your waste facility. And then finish by just covering off some common pitfalls that we've experienced in terms of the mine waste characterization. So just a brief overview on what the geochemical risks are with mine waste. They are typically associated with the surface waste, obviously the waste rock, tailings, the material that's still remaining in your pit walls, and obviously also your underground workings and the paste backfill material. And basically is always a result of your metal sulfides that are brought up to the surface. The sort of most common are pyrite, galena, chalcopyrite, and they're brought up to the surface and basically exposed to oxygen and water, and they undergo chemical weathering and basically result in the release of acid rock drainage and metal leaching. And the diagram there just shows some sort of typical sources and pathways of acid rock drainage and metal leaching, commonly abbreviated ARDML. Obviously, as the material's also brought up to surface, you're increasing the surface area as well. It's another sort of key point to note. So you're increasing the surface area subject to weathering, and hence the potential for ARDML. The diagrams here just, again, just give a brief summary of the geochemical risks. So the left-hand diagram gives you a typical open pit surface example, and the top is your stable system. Obviously your material is underground and stable prior to any mining starting. At the point that mining commences, you have your sulfide material being brought up to surface. Your waste material is going into waste rock dumps, or it may go into processing and then hence end up in your tailings. And all at that point being subject to your weathering, exposed to oxygen and water, and hence release of ARDML. The diagram on the right-hand side gives an example in terms of underground mine. So the left portion of that is sort of during operations, and during this time, there's the possibility that sulfide material can be exposed in the wall rock of your underground mine. Obviously, oxygen is getting in via vents, shafts, and adits. And there's the possibility that oxidation products can accumulate on those wall rocks underground. Now, if you do have an inflow of groundwater at any point, there's the possibility that this can flush out those oxidation products. and the resulting water quality is going to depend upon the contact time of that water and also obviously the reactivity of your material. But there's a possibility that that water may require treatment prior to being released. The other portion of the diagram there is after closure. Typically we've seen that waste material is stockpiled on surface whilst the mining is underway, and then at the point that the mine is closing, that material is put back underground. Whilst the material is at surface, again, it's obviously being exposed to oxidation, weathering, and again can accumulate those oxidation products. As the material is put back underground, the groundwater levels are allowed to rebound, and again you can get this flushing of the oxidation products to groundwater. So why the need for the waste characterisation? There's basically a twofold requirement to this. Firstly, it is required by legislation. So the main legislation, as Jane mentioned, the EU Extractive Waste Directive, also referred to as the Mine Waste Directive. And the second sort of reason for the waste characterisation is really to understand and manage the risks to your project and do that as early on as possible. So considering just the legislation side of things initially, the Mine Waste Directive 2006-21 EC calls for a waste management plan, which basically identifies your management methods and classifies your waste storage facility. I've included the waste hierarchy diagram there, because obviously their ultimate aim is to recycle and reuse the material. And I'll mention in a little later on as how geochem can help you do that. But as part of the waste classification, you're classifying your facilities. You are also assessing your environmental and social impacts. You're putting a plan in place for your monitoring procedures and also planning for closure. So the waste characterisation itself requires numerous different legislations to be followed, numerous different documents. Initially, waste is given a European waste code, which is non-mining specific, so the can be open to subjection. It's designed to cover all different industries. Secondly, the material is classified normally as inert or non-inert, and this is done predominantly on the concentration of sulfides and heavy metals within your material. There are other factors as well, such as combustibility, but the sort of main items that affect our mine waste is the sulfide and heavy metal contents. And the hazardous classifications are assessed, hazardous characteristics are assessed in order to classify your mine waste facility. The hazardous documents, again, are a non-mining specific legislation, so it does span numerous industries. We have come across quite a lot of examples historically where there's been confusion on the interpretation of this, and the EU have actually recently just published a guidance document on that, which literally came out in the last month, so hopefully that will clear up some of that. The inert, non-inert and hazardous all go into then classifying your waste facility, but you must also obviously consider the physical and chemical stability of your material under the surface conditions. And you need to ensure that you're still investigating those environmental impacts in terms of soil, air, ground and surface water. This is particularly important because the inert, non-inert, hazardous classification doesn't actually specifically address the environmental impacts, but it is implicitly mentioned in the Extractive Waste Directive. It's important also obviously to note that I mentioned the physical stability. My presentation is mainly focused on the geochemistry, but the geophysical side of the material is equally as important in the mine waste classification. So considering the sort of second part of the need for waste characterisation, to understand and manage the risks to your project, so separate to the legislation, it's worth noting really that the geochemistry study can ultimately drive the design of your project in terms of your waste facilities. It's really important that it is considered in the early stages of mining. It shouldn't be sidelined. It can ultimately be used to determine what materials can be reused for things like railroad building, and obviously this ultimately reduces your waste and your closure measures and hence your costs. It can be used for predicting impacts and predicting them up front, which is allowing for engineering designs. It's much better to manage your risks up front. It's normally cheaper to do your risks up front rather than pay costly mitigation later, such as treating a leachate. And typically things like liners can only really be placed before your mining has commenced. We sort of feel as well that finances have a high interest in the level of geochem study that has been done and how that's influenced your mine design, really based upon the understanding that pollution risks and long-term liabilities can often be related to geochemistry, and the environment issues came up in the finance discussions yesterday. So how the characterisation is actually done. As I said, there are numerous legislation documents. There are quite limited prescriptive EU guidelines on the methods actually needed for the waste characterisation. Some of the legislation are specific to mining, such as the Extractive Waste Directive, Mine Waste Directive. Others are generic to various industries and for that reason can be potentially open to misinterpretation. There isn't specific test methods often given in the legislation documents. There are sort of international best practice that are typically followed. So some examples are the GARD Guide, the Global Acid Rock Drainage Guide, and the MEND report, the Prediction Manual for Drainage Chemistry from Sulfide Materials. The number of samples, again, aren't normally defined in legislation. This often depends on the geological complexity of your project and also what phase your project is in, such as your PFS, FS. The GARD Guide, for example, suggests that several hundred samples should be taken at PFS level for your geochemical study. Often it's dependent upon budget constraints as well as your project. So as part of the characterisation process, obviously it needs to comply with that legislation, so you need to ensure that you are able to then fit your waste into those prescribed categories, your inert, non-inert, hazardous, but you also need to ensure that you're assessing that future environmental impact. And as I alluded to earlier, that is included in the Extractive Waste Directive, but not explicitly covered in the classification of the mine waste facility. Your sample selection needs to be representative of future waste, both spatially, you need to get a good spatial distribution and geological distribution. You need to ensure that you're covering all lithologies you're likely to encounter. You should get a range of weathering, different weathering states. Obviously, you're targeting your waste material and not the ore. The number of samples is site-specific, and it can be useful to have an estimate of the proportion of lithologies likely to be present in the waste. So it's useful to have discussions with your mine planners, and this can assist you in targeting the right proportions of samples when you come to do your test work. May also be useful to consider assay data. We quite frequently use sulfur data to ensure that we're selecting our samples with a range of sulfur contents, so you're not biasing your sample selection towards the high or the low end. Obviously the sample selection and the geochemical characterization is typically done prior to any mining commencing. So these samples are normally collected from exploration drill core and obviously reliant on whatever assay data you have for that exploration drill core. So during the waste characterization, you undergo a number of different test methods. The ultimate aim of these is to quantify your total reservoir of acid generation and metal salts, to quantify the reactive portion of your waste, and hopefully quantify the rate of leaching and acid generation. Now, the process of these lab tests hopefully allow the identification of problematic but also your good lithologies, so it enables you to identify your material that doesn't have to be specially handled. It can be used for road building. And the tests sort of fall into these two categories. So you have your static tests, the shorter term tests. These are designed to give you an idea of your total potential for acid generation and metal release. So they include assays of your bulk constituents and your acid generating sulfides versus your neutralizing carbonates, to give you an indication of what is there overall. These are typically lower cost and they run in the order of weeks to do. Then you have your longer term kinetic test works, which are then designed to try and get you your rate of release, so your rate of acid generation or metal release. And these can be lab scale humidity cells, is the image that we've got there. These were run at Cardiff University, and humidity cells can run for a period of months. They're designed to simulate and accelerate field conditions. And then you can also have field scale cribs where your waste material is left on site, so subject to actual site conditions, and those can run in the order of years. Hopefully the results of your kinetic test work can then be used in your water quality predictions when you come to do your modelling stage. So the influence that the waste characterisation has on your waste facility. The Extractive Waste Directive defines the time that material can be stored on surface before it has to be considered a waste. This is very dependent upon the material characteristics. Obviously, the more hazardous your waste, the more stringent the requirement is. This is really important in terms of the backfill waste that obviously is coming up quite a lot in discussions. Typically, backfill waste is stockpiled on surface, and we have come across examples where that material hasn't been classified because the intention is to eventually move it back underground. But the Extractive Waste Directive does specifically state that it needs to be classified as a waste facility if it is on surface for these periods of time, obviously depending on the characteristics. So if your material ends up being classified as hazardous, it ends up in your facility category A, which Jane mentioned the requirements for the category A earlier. Other criteria can trigger a category A, such as implications of failure if the waste facility was to fail. The category A is quite well defined in legislation. The difference between the inert and non-inert is not so well defined, but some national guidance does recognise this. I think we've come across this in some Irish guidance. Talking about the excavation voids for your backfilled waste. Now, typically excavation voids are not classed as a waste facility, so you don't need to officially classify them in terms of the way you would with a waste rock pile, for example. However, the Extractive Waste Directive does have a section where it specifies that the extractive waste void must not produce any subsequent environmental impact. Therefore, it's still essential that you're characterising your waste that you intend to put back in that excavation void. So although it's not covered under the facility side of things, you still need to assess the environmental impacts. So some of the common pitfalls that we've come across in terms of the mine waste classification. I talked a little bit earlier about the allocation of the European waste codes, and there is a waste code which is features right at the top of the list. It's 010101, which can be applied to waste from mineral metalliferous excavation. This obviously covers quite a lot of our mine standard waste rock material. And this waste code is classed as an absolute non-hazard. What that really means in terms of classifying your facility is that you don't actually have to then do any further assessment on that material. So the danger is, and we have seen it done, that you allocate that code and you leave it at that. However, the Extractive Waste Directive has that other focus where you need to assess those environmental impacts. So basically, you cannot just allocate that code and do no further environmental assessment on your material. A lot of the legislation in terms of the inert, non-inert and the hazardous focus on the concentrations of solid in your material and give minimal consideration to the leachates. Obviously, there's the leachates that pose the highest risk really to your water quality, and hence the need for the holistic approach, considering your environmental impacts alongside just the waste facility classification. I've mentioned already the limited consideration of backfill waste. So this can be failure to classify your waste while it's being stockpiled on surface, or failure to correctly classify it when it's being returned underground because that excavation void isn't officially a facility. We've come across numerous difficulties in interpreting the complex legislation. As I said, this spans numerous documents. These are updated frequently. Some are mining specific, some are not. So there can be difficulties just arising from the interpretation of the legislation. Another thing is sort of getting the representative samples early on in the mine design. This is particularly relevant for tailings material, where the mineralogy can change quite dramatically throughout the course of the mine life. And it can be difficult to obtain those representative samples early on when you want to assess that material. So just to summarise, there we've said that waste characterisation is important because of that twofold approach. So it is required by the Extractive Waste Directive, but it is also essential to drive your project design. It provides opportunities to manage risks in your project upfront, both through mine planning, your design, and through engineering and monitoring. EU legislation calls for the classification of your facility and your waste that goes into that facility in terms of inert, non-inert and hazardous, and it calls for management of the environmental impacts. So you must follow it correctly, you must have the holistic approach and do both. And specialist input we found is required. Every characterisation plan needs to be site specific, and you need to ensure that you're right from the beginning that your sampling plan is relevant to your particular site. You need to ensure that you've got the correct test work methods in place. We've come across examples where the correct methods have been applied, but key parameters have been missed off. The limits of detection have not been low enough, or the application of those results haven't been correctly interpreted in terms of the legislation. Thank you very much.
Hi everyone, thank you for waiting back right to the end. I appreciate your time. So yeah, my name's Jamie Spears. I'm a senior tailings engineer with SRK based out of the UK. And yeah, today I really want to talk about minimising operational risk through effective tailings stewardship. There have been a lot of high-profile tailings failures recently, 3 within the last month actually, and these have occurred in developed jurisdictions like Mexico and Australia, and we really need to drill into the reasons why these are occurring and ways in which we can minimise the impacts of these failures. So, as discussed, some recent high-profile failures have put the mining industry under intense scrutiny over the last few years. And evidence suggests that many of the causal factors share a common theme, and steps could have been taken at a much earlier stage to avoid or reduce the consequences of failure. Typical risk factors common to many tailings facilities include operating a tailings facility contrary to design, and this can be driven by time constraints, poor technical understanding of the facility by the operations team. It's not their job to understand the ins and outs and what makes a tailings dam tick, if you like, but they have not been provided with the information required to adequately operate their facility. And cost pressures. We've all been exposed to situations where we need to raise tailings dams quickly and efficiently, and often to defer capital. Many operations leave that until a point at which it becomes dangerous to operate the facility. Simultaneous embankment construction and tailings discharge into the facility can create issues. Municipal water dams, for instance, are developed or constructed in one raise and to a very high standard. So typically water reservoirs are not exposed to the same issues that tailings facilities face. Lack of communication between a design team and operators can lead to issues operationally, and lack of inspections by independent experts and independent engineers. Monitoring, and the key thing is understanding monitoring data and what it means. That's a critical component which we'll touch on later. And lack of documentation. In the EU, we use operational and maintenance manuals and monitoring plans as standard on all operations. So frequent occurrences of these practices have led to resulted in a greater emphasis on technical and environmental stewardship of tailings facilities. So this, I've put up this graphic here, which is quite interesting. It shows the tailings dam failures occurrences over the last 100 years. And as you can see, there was a spike during the 1960s and 70s of tailings dam failures, and this is really attributed to a rapid increase in that period of boom and bust cycles of mining, rapid increase in ore production, and obviously the associated tailings generated with that rapid increase. More throughput means more tailings to store, and during the 1960s and 70s there weren't these serious or well-developed protocols for tailings stewardship and design codes in place, and the weak regulatory regimes, I would say, in a lot of jurisdictions led to this spike. And notably, over the last 20-30 years, there's been a significant reduction. So we're getting better at tailings management and stewardship, if you like, but we've got a lot to do. That should be reduced to zero. It is unacceptable to ever have tailings failures. So what are the causes? These charts really indicate the changing causal factors over the last 100 years. And I think a key point here is that recently it's this wedge of the pie chart here. It's the poor management is becoming a key contributor to TSF failure. Also weather. We can't influence the weather, but poor controls on excess water and surface runoff into your facility could also be considered a poor management practice. And both of these together contribute a significant chunk of the causal factors for tailings failures based on this particular research paper. Right, so typical failure modes. This is really a high-level summary at this stage, but in the foundations, weak clay layers or weak rocks and soils, which may not be identified during initial geotechnical investigations, can lead to erosion in the foundations. Piping and karst features in limestone environments, sinkhole formation can lead to failure of the liners beneath those facilities. And liquefaction. Liquefaction, in a nutshell, is the process of loose, wet, coarse tailings or sand material acting in a contractive manner during loading, and this causes the material to lose strength and behave in a liquid manner and flow, and this can cause significant issues with tailings facilities, especially in seismic regions. In the dam itself, liquefaction can be an issue, increased pore water pressure due to poor water control, and deformation of the embankment. And settlement of the embankment can lead to overtopping. It's particularly in seismic regions such as this. and design measures need to be implemented to avoid that occurrence. Overtopping on water, this is the major factor. Poor water management, leading to issues with freeboards, but also high water levels in the embankment, which can reduce the stability of the embankment and lead to failure. And environmental failure modes, equally as important. Inadequate design of seepage control measures, whether those are natural clay barriers or synthetic geomembranes, seepage from the embankments, and excessive unplanned release of water from the facility. Emergency spillways are designed to quickly release water from facilities during an emergency event. However, what is the water quality like, and can it be released? And frequently it cannot be released, or it shouldn't be released. We see it over and over again. Discharge of water which is not fit to be discharged to the local water courses. Obviously, poor water control can lead to excessive dusting on top of the tailings facility, and that can cause erosion as well. So the cost of failure, the most important ramifications of failure are obviously loss to life and environmental and social effects. This is why we do what we do. We stop these things happening. But the physical costs of remediation are very high. These can range from millions to hundreds of millions in the immediate short term. The environmental cleanup, times that by 10, it could be hundreds of millions. As we found at San Marco in Brazil, the current estimate is $7.7 billion US to remediate the outcomes of that failure. So it's going to affect your bottom line. Closure liabilities frequently catch operators and facilities which have not been designed with closure in mind, particularly groundwater and contamination issues. Groundwater contamination, dealing with that into perpetuity can cause significant issues. And the costs can go from hundreds of millions into billions. And obviously there's the immediate impact on shareholder value of companies. Following a tailings failure, when it was reported in the press, you can see immediately the share price plummets, and this can really have knock-on effects. Okay, so I'm going to talk about a specific case study, the Fundão tailings dam failure in Brazil, which occurred in 2015 by means of a case study. So this is a general arrangement, and as you can see, the key notable features here are in the left abutment, a setback in the facility, in the main embankment, slimes and water storage area at the back of the facility, and an upstream raised main embankment. This embankment was constructed of coarse tailings material, and the slimes, the design intent was to keep slimes and water away from this main embankment. Okay. So the failure itself happened on the 5th of November, 19 immediate deaths, one of the worst possible ways to go, I'd imagine, and the people in the villages downstream of the dam would have had minutes to respond. Completely impossible. There were significant downstream effects, not only in the communities and the immediate fatalities, but the rivers and the environment, which are still being remediated. In the immediate aftermath of the event, the local reports indicated an earthquake had caused the dam to fail. And this is a before and after picture which really highlights the horrific kind of consequences of the failure. The main embankment's completely gone, a flow-out failure, and this failure propagated back in, so it's very hard to stem the flow when you've got millions of cube of water and slimes material which mobilises instantaneously. There's nothing that can really be done to mitigate that. And these pictures really just highlight before and after what happened to the communities downstream. The river system, which runs, the Rio Grande River, which runs all the way to the Amazon, hundreds of kilometres. The inundation zone actually extended hundreds of kilometres to the Amazon itself and clogged the river system with iron ore slimes and coarse rejects. Obviously, there's the immediate impact on the ecosystems and the biota, but one of the most pertinent things for me was the fact that tens of thousands of people used the river itself for food supplies and potable water supplies, and within hours, this dam break propagated the whole way down to the Atlantic and wiped that out immediately. So you can imagine the impact on the local populace. Okay, so expert panel was convened to investigate the cause. This was an experienced team of tailings engineers, geotechnical experts and seismologists. And the purpose of the investigation was really to look for a failure mechanism. It was not to attribute blame or to give people means to take litigation. It was really to look at technical reasons why this happened. It was undertaken by independent engineers, and the report was issued in 2016. It was an extremely clear and unambiguous report to be used by all stakeholders. I'd really encourage you all to, anyone who's interested, to look at the Fundale investigation report. The link's there. Another point I would just make, there's a legal case ongoing and litigation ongoing with this failure. So by all means, refer to this presentation. But please, if you're making reference, don't reference my presentation, which is based on this report. Please reference the actual report itself if you're going forward. So the initial design of the Fundale tailings dam, let's investigate what happened. It was an upstream raised design. As you can see, these were two options that were looked at, a centre line raised design and an upstream raised design. The latter was selected as the most appropriate. There was a separation of sands material in the coarse shell and slimes material located away from the facility. This separation was key and paramount in the design documentation and should have been honoured throughout the operation. Drainage galleries were constructed, so basically drainage underground tunnels to divert perimeter flows of runoff each side of the facility, clean runoff. And a 200-metre wide zone was maintained or stipulated in the design documentation. The purpose of this really is to maintain a coarse, well-drained shell which will not be prone to liquefaction during a seismic event or even during a process called static liquefaction. And construction equipment and vehicles can induce liquefaction in these materials. So a 200-metre wide zone acts as a buffer and prevents that occurrence happening. And this is the general arrangement before deposition. You can see the two drainage galleries around each side, and the main embankment and a separate slime storage area to maintain a minimum offset from the main embankment. Okay, and this really just highlights the concept of beach above water. Deposition should have always occurred on drained beach above water, and ponded water and slimes should be kept separate. So the immediate causes, the report identified as the initial cause a liquefaction flow slide which occurred in the dam's left abutment zone. So let's remember there are two types of tailings: granular sand tailings, which is free draining, but if that's loose and saturated, it can be prone to liquefaction. This can lead to strength loss and the material flowing like a liquid. The slimes material located inside the main basin of the facility has a finer grain size, but if you load that material, it becomes soft and compressible. And it can lead to, the key thing, it can lead to settlement of that material, but also the vertical permeability of that material reduces significantly. And that, as you'll see in a second, leads to additional reasons, or additional problems. So the dam design required that these two types of material be kept separate, but a series of unplanned occurrences occurred. The original starter dams failed, the drains within the starter dam failed, and they were subsequently sealed up. A piping failure occurred, and a soils piping, internal erosion of the dam. Slimes were deposited in the in the coarse shell, which they shouldn't have been, and therefore that resulted in slimes and water encroachment towards the main dam. And the final piece of the puzzle was one of the drainage galleries, and the left abutment failed due to loading of the tailings. So these unplanned occurrences led to a change in the dam alignment. The setback, which I highlighted at the beginning, was instigated. And this led to loading of more material on zones which were previously defined as slimes only areas. Tailings embankment was constructed on the slimes, and it led to saturation of the slope shell. The consequences of this were compression and lateral extrusion of the slimes. The best analogy for this is toothpaste being pushed out of a tube in a horizontal direction. And what this did was this mobilised the sand material overlying that, and it became torn apart and progressively looser, which set up an occurrence or a trigger mechanism for this liquefaction event. Okay, and this would have happened over a long time. It was a progressive failure that was occurring, a progressively got looser and looser and looser, more and more saturated, and therefore prone to liquefaction. And the final straw which broke the camel's back, as it were 3 small earthquakes which hit in close succession, and that initiated the process of liquefaction. So these pictures show during startup internal erosion on the starter embankment. You can see the fines material which is migrated out of the embankment, which indicates internal erosion of the dam. The drains basically were not installed as they should have been. And in the left abutment, this setback, the engineers wanted to get in to remediate the drainage galley in the left abutment here, but in doing that they were stepping on slimes material, which was a big no-no. So these cartoons really highlight the process that was occurring. Slimes material was deposited in the 200-metre wide coarse shell. This led to vertical permeability of the material being reduced and an increase in the phreatic surface. As the setback was constructed on the material, the slimes zone was loaded with more material, and this led to this lateral extrusion or squeezing of the slimes material, which moved forward towards the main embankment. And this resulted in dragging of the coarse sand shell and loosening of the coarse shell. And with the high water level and the saturated conditions, the seismic event hit. The material contracts instantaneously, the pore water pressure increases, and the material loses strength. And therefore, the whole embankment lost strength, and there was a flow-out failure. Okay, so the outcomes of the review were that management of water is a primary concern on all tailings storage facilities. Changes in design and operations during lifetime are required. I mean, as operators, you'll all be very aware of this. Designs have to be modified as you go along. But these changes have to be understood, and the designs need to be refined appropriately to deal with that. Design of or drains or dams that are located, drains which cross dams or are located beneath tailings themselves will lead to potential difficulties in the future and are prone to failure. And constraints placed in designs must be followed during the operational phase. Inspections and monitoring are required, and a protocol needs to be set up, a link between inspections, monitoring and trigger levels, and required actions following on from that. You need to action issues that are being indicated by your monitoring data. Okay, so moving on from that, good practice tailings management. Water management is a key issue, and we need to design for larger storm events. This is partially as a result of climate change. The climate is becoming more variable and less predictable. You need to design for large inflows of water in your tailings facilities. In reality, that's very expensive to do. Class A facilities need to be designed for closure. You need to consider probable maximum floods. Those flows can be very large, and the earthworks associated with designing diversion channels can be massive. So it's not an easy feat, but water management is the one take-home message that this needs to be dealt with during operations. Strong operational management is required, and documentation needs to be in place. In the EU, we expect at tailings facilities operations and maintenance manuals to be prepared, and monitoring plans as a minimum associated with tailings storage facilities. We can't step outside the design constraints of the facility. Robust monitoring systems need to be put in place, frequent inspections by tailings practitioners, and closure design needs to be thought of at the earliest possible stage to avoid those huge cost liabilities which could incur at a later stage. And ongoing communication needs to occur between design engineers and mine operators. Mine operation staff change, design engineers frequently change throughout the life of a mine, which could be 50, 60 years. That continuity needs to be kept there to avoid these occurring. So water management, I've said that this is a hugely important component, which is a causational factor of failures. We need to understand, some common practices which are observed are not understanding freeboards and the limits of the facility for storage of water, using the TSF as a water storage facility. We all know that we can reuse water in the plant, but tailings dams are not designed to store water, they're designed to store tailings. We should be getting water off them as quickly as possible. Overfilling the embankment raises to delay capital expenditure, especially during upstream raises. Operating the TSF contrary to design, and in doing this, depositing tailings beneath water, for instance, can lead to a lower storage density and the rate of rise increasing to an unacceptable rate, which can lead to operational difficulties. Inadequately designed perimeter diversions. We saw the issues that they had at San Marco, which ultimately led to them stepping back to try and remediate their perimeter ditch. Your diversions need to have capacity to divert large slugs of water, which could impact your facility, and insufficient monitoring. We'll talk about that later on. Maintenance of water recovery systems is also paramount. Your penstocks, your floating barge decants, your emergency spillways, those all need to be maintained to a very high level. So this is really just a case study which I brought in to highlight what we really should be thinking about during the operations phase in terms of water management and how we can mitigate this risk of reaching your freeboard marker and putting the dam at risk. This was an operation we helped out in West Africa. And basically what we did here was we had a perimeter discharge facility, and we came up with a design to switch it from perimeter discharge to a central discharge system. And the main reason for this was deposition for closure. So use your tailings to create a convex surface which would shed water at closure and could be rehabilitated. This reduces operational complexity, but also reduces closure cost. If you can create the convex surface to cover, it's going to save millions and millions of dollars bringing in imported fill to construct a cover system. So it's a risky process doing this. You're shifting your pond from a nice central location, well away from the perimeter embankments, to a perimeter area, a peripheral area. So what did we do? We did 3D modelling. We used Muck 3D software, which is kind of rapidly becoming an industry standard for tailings deposition modelling. And we looked at how the beach and the pond would migrate over the final years of operations. And in doing this, it allowed us to design an emergency spillway system in the southeast flank of the facility, which would ultimately act as an operational control on water, excess water, but also at closure. Once we've covered it, and this light orange area here, we can actually remove water effectively into perpetuity, if you like. So this is an indication of the water balance here, and you can see the seasonal variation per annum. And we've mapped the water level in the graphs here, and it shows clearly water level over time, plus our freeboard marker and plus our crest elevation. So this allows us to design a system, and that gives the operator advance warning so that they can continuously raise their embankments well ahead of the water surface, and there should be no ambiguity over how and when to raise the embankments during that period. But the key point is that in doing this periodically throughout operations, you can bring this back into your operations plan, and it just gives the operator that sense of assurance that you're not creating an issue, or you're not about to imminently reach your freeboard marker, if you like. So briefly, the documentation which is typically considered or used in the EU is an operations and maintenance manual. The Mine Waste Directive requires that all facilities are constructed, operated and closed appropriately. And to achieve this, an operation and maintenance manual should really be prepared as part of the waste management plan. And the waste management plan was referred to by Jane and Mel earlier on. This document is usually submitted to the authorities during the design stage to get planning permission or whatever the local equivalent is in EU member states. And this document provides the operator with the necessary information necessary information to operate, monitor and manage emergency situations. The manual needs to be regularly updated throughout operational phase and ideally integrate water balance information. And the manual should include, as a minimum, a detailed description of the facility, critical elements such as freeboards, pond levels, seepage volumes, stability and performance data, such that the operator understands what makes the facility tick, what key things they need to look at. Details monitoring instrumentation, inspections by the operator, pro forma documents for that purpose, And the key thing is there are emergency response protocols in there for unplanned or untoward events. This document allows effective communication of the design intent with the operator, and it reduces the likelihood of the TSF being operated in an unsafe manner. Emergency action plans, these are tagged on to operational plans usually, and this documents the procedures that staff should follow in an untoward event. That's interestingly at the SRK failure, I mean, it should never have got to that stage, but the people there had minutes to respond, which would probably in reality be impossible. But if there was a monitoring, well, I'm not sure what went on, I can't comment at SRK, but emergency action plans are designed to give everyone downstream, all users, a fighting chance to respond as quickly as possible to emergency events. So this is an example of a dam break analysis, a public domain one. But typically these are prepared to indicate inundation zones, so we assume that a dam has failed, and we do 3D modelling to indicate how far and how deep and how quickly a tailings flow will propagate from a facility. And in turn we can use this to plan for emergency action in the event of a dam break. So the emergency action plan should be linked to the operations manual, and there should be different levels of response. A hazardous condition or incident which could develop, a potential dam emergency where communities have to start taking steps to prepare for evacuation, and obviously an imminent emergency, and evacuation procedures should be in place for that. So the EU Mine Waste Directive and best available techniques recommend that this is in place as part of your operations plan. So briefly I'll talk about, to finish off, inspections and monitoring. In the EU, competent authorities are obliged to carry out regular inspections. The inspections are the responsibility of the operator, but they need to be done in accordance with the Mine Waste Directive. So operators tend to use, or should use, independent experts to perform the inspections and supervise, improve and audit the facility and make sure that it's being continuously operated in line with best available techniques. These should include regular inspections of the lagoons and the embankments, and we can look for potential failure modes early on. They should include an inspection of the decant and water management structures. I highlighted the importance of that in the previous slides. And particular attention should be paid to pipelines which are laid directly through embankments. This is decant in this particular sketch anyway. There's a penstock which extends through the embankment. These typically extend through embankments and the foundations, and what we see again and again is soils piping or internal erosion around these pipes where water's flowing along, and this can lead to basically progressive internal erosion into the tailings facility, which can cause very, very quick failures to occur. Other failure modes we're typically looking for during inspections are settlement along the crest, which could result in a reduction in freeboards, cracking, slumping, rotational failures, seepage from the embankment. All of these failure modes, plus inspections of the water storage or water management facilities, are required. The key point to remember here is that the EU Mine Waste Directive recommends these happen at least on an annual basis. So consultants cost money, we understand that. You might argue cost you too much money, but a yearly health check, if you like, on your tailings facility pays dividends in the future and gives you the assurance really that you're operating it within the design intent. Monitoring systems, you know about monitoring systems, I won't labour on this, but standpipes and vibrating wire piezometers in water retaining embankments are really a minimum to monitor pore water pressure continuously. And the data should be regularly plotted against rainfall data and pond levels and tied back into the water balance, similar to the charts I plotted up earlier on that particular example. And we need to compare that data to trigger levels. If the water level hits a trigger level in the main embankment, everyone responsible, the engineer of record, the mine manager, needs to know about that so that action can be taken quickly. Seepage quality should also be monitored, and the quantity as well, how much is leaving the facility. And again, that ties back into your water balance. And finally, inclinometers are very useful. They give an early warning indication of lateral movement and a potential slowly propagating failure which could impact the facility. So this final slide really just is to highlight the importance of not just gathering and monitoring data. Most TSFs we visit these days are gathering lots of good monitoring data, but you need to use that data and you need to visualize that data effectively. A number of our clients and a number of mining houses are developing cloud-based systems to manage data. Depositories for data externally from the mine, which can be shared and scrutinised by all the staff members, whether it be at the mine site itself or in corporate offices or by the design engineers. So the data itself can be manually or automatically uploaded via data loggers. We have wireless technology on most sites now, so there can actually be real-time update of information. And this was an example of a project up in northern Canada. And, oops, sorry. As you can see, we've got a tailings storage facility and we've mapped out the piezo locations. You click on a piezo location, you can look at groundwater level charts, water quality charts, various metrics related to that piece of equipment. And when you click on one of those, water level chart comes up for the past period. You've got your freeboard level, your crest level there, and should that exceed a certain trigger level, it's graphically illustrated for all to see, and remedial action can be taken. A neat part of this system was when those trigger levels were reached, an alert email or text message, SMS, was sent out to the mine manager, the engineer record, the design engineer team, so that immediate remedial action could be taken. And this, in theory, should significantly reduce the risk of these creeping style failures occurring, or creeping water levels, or reducing the stability or a factor safety of stability on your embankment slope significantly. So there are also CQA tools there as well to make sure that all the data that's been inputted is standardized. We have a lot of problems with randomized entries going into monitoring data, which can really cause a lot of consternation on site if data is entered wrongly. So this system helps that happen. So the take-home message here is that this is something that industry is moving towards. If you have ways in which you can visualize your monitoring data and have a real-time indication of what's going on in your facility, there should be no excuse to not action remedial action very quickly, and it should make us reduce the risk of tailings dam failures down to 0 rather than 8 per annum, which is what we're currently sitting at. So yeah, so that's really everything from me on that topic. So thank you very much. So were there any immediate questions from anyone or for any of the topics on the legislation or the geochem or the operational management? There is a microphone at the back. Great, thank you.
Thank you. This could be either for you or for your colleague. And that is, what about a country that's not in the EU, like Macedonia, where it has existing mining investors from outside or potential future ones that, do they have to comply with this EU guideline? And if they have already started, are there retroactive measures that could be taken for compliance, whether by the EU or by the local government or others? So how they have to factor that in with their risk or their planning?
Yeah, well, I could start the answer. Please jump in on the mics if you need to. There's no obligation outside EU countries to take on these systems. But what we tend to do is revert to best practice Canadian, Australian guidelines wherever possible if there's no kind of local legislation. Countries like Macedonia do have legislation in place. Disingenuous to say that they didn't have these standards. And in some cases, I'll use the example of Ghana, for instance, in West Africa, very different to Macedonia, but they've actually got higher standards for embankment stability than factors of safety than we typically use in Canada and Australia and the UK. So it varies dramatically per country. Russian legislation is very specific as well. They use very different methods for analysis. So a big part of our job is trying to synergize different codes and different mechanisms and looking at the best approach. But the neat thing about the EU approach is it's a risk-based system, so you don't just characterise your waste, but you look at what the potential impacts are going to be in groundwater. You do the field investigations to characterise your aquifers beneath the facility. You do modelling to show that even if you've got tailings which has metals mobility or potential for acid generation, that it's not going to impact your groundwater system. Have the data there to back up, and the key thing is getting that data in the first place to back up your assumptions, and you can go to your regulator in whichever country it is and say, look, this is based on evidence and based on data, and we spend a bit of money doing the modelling on this, but you can show the regulator that you've been stringent in that approach, and therefore it's possible. So there's no prescriptive guideline and no system which is best. Key components are good from different systems, but have the data and do the analysis really to back up your assumptions.
But can I add to that most Balkan countries are undergoing accession to the EU. Those countries that are undergoing accession to the EU are transposing the EU legislation into their legislation. So this is the future. The countries that are closest to the accession, Montenegro, Serbia, that will be what they have to follow soon.
Definitely. Any other questions?
I have one question. I think Melanie addressed this issue related to the non-hazardous and hazardous waste, the categorization, classification. As we know, the waste code label these waste, different waste streams, according to the origin. From there they are coming. For example, mining of gold or mining of copper and so on, and the process, how it is exploration of the metals. You mentioned that it is not enough. So the classification, maybe it is according this waste code, the waste is labeled with non-hazardous, but after that the physical and the physical characteristics and impact maybe will label this waste as hazardous. Do you think this Seveso classification according this European Chemical Agency classification as a hazardous mark, these things? Or maybe I'm wrong. When you mentioned this, I was thinking about this categorization, but maybe I'm wrong.
Yeah,
please clarify.
The hazardous classification, it isn't MINEX specific, so you mentioned the Chemical Agency database, and it's kind of designed for companies that are transporting chemicals throughout Europe. So often the codes, the waste codes are given relating to sort of non-specific mining waste. The difficulty comes with mine waste is the fact that the Extractive Waste Directive says that you have to still classify according to the environmental impacts. So the giving it just the waste code is sufficient in terms of classifying your facility. However, it doesn't address the other aspect of the Mine Waste Directive, where you must also assess the environmental impacts. So did that answer your question?
So it depends on the environmental impact. If you decide to classify as a hazardous or non-hazardous?
No, so you have to do both. So you have to do both. So the inert, non-inert and hazardous classification is really to determine your facility. So if it is classified under those characteristics as hazardous, you must still have a category A facility. If it is classified as non-hazardous, it doesn't necessarily mean that that material doesn't have to be treated in a specific way. So non-hazardous material may still then have the environmental impact that it's going to generate a leachate that's heavy metal content. So hence the need, you need to do both. You do the hazardous to classify your facility, plus you assess the leachates in terms of the environmental impacts.
Just a short question: in what circumstances rock waste landfill can be characterized as a facility?
Sorry, that was what categorises it as a, yeah. In terms of the geochemistry, it is having contents that are above particular thresholds, and there's EU legislation documents that basically assess hazard properties. There's, I think, 15 hazard properties off the top of my head, and they look at contents of your waste in terms of the carcinogenic properties. It's basically assessing the dangerous properties within your waste. So if your material is above particular thresholds for any of those hazardous properties, it is classed as hazardous and has to go in a category A. But there's also other aspects like the implications of failure of your facility. So if your dam is going to fail and it's going to cause catastrophic events, then that also is enough to classify it as a category A facility.
Again, but you're talking about a rock waste landfill or tailing?
Both. It applies to, yeah, any of your waste material.
So just to add to that, I mean, I guess if you've got hazardous, material in your waste rock, essentially, and you're storing that in a facility, something we've worked on before is, can you put that material back underground and co-dispose it with paste? And if you prove that that material will not have any impacts through seepage on groundwater, then that material suddenly becomes a construction material, and you're placing material in an excavation void. You're using it for geotechnical support underground. And if indeed you can prove that there will be no impacts on air, water or seepage, then that is actually in line with the EU best practice, is to reuse waste and utilise it for an underground operation. It saves you bringing in material from elsewhere for your stope support when you're doing your underground mining, for instance. So that's quite a neat way to deal with category A material. It's in line with the EU essence of the guidelines. It's been reclassified, if you like, but again, the technical studies have to be there. So do a lot of geochem testing on it, create paste backfill samples, do cemented cylinders, run monolithic leach tests on those for 3 months and prove that there's going to be no seepage from that material, and your waste rock becomes a underground support medium, if you like, rather than actually being a waste facility which has to be managed on surface, potentially for a long time. Any other questions? Just a final point I was going to make, it was interesting that the questions that all came out were related to in-pit disposal and dewatering of tailings. And the industry is certainly moving towards dewatering of tailings to reduce geotechnical risk. And the key thing, I think, is coming from whether that's a geotechnical risk or whether that's a geochemical risk or environmental risk through seepage. The key point is that looking at ways we can be smarter about keeping water in the plant and not sending it out to the tailings facility is really what we're striving towards at the moment. And certainly a lot of EU best available techniques worldwide are looking at kind of minimisation of impact of water. But interestingly, I sat at an ICMM meeting a few months back, and the key point was that whilst going to, I think the mission statement was, how do we move towards no moisture in water, in tailings, sorry, so basically zero water in tailings. And a lot of the operators really said that was a great aspiration to strive to, and all agreed it would reduce the geotechnical risks, but it's got to be a site-specific thing. The costs can be precluded, can reduce the effectiveness of that. A lot of mines possibly just couldn't actually get off the ground if you were to filter all your tailings. It's a very expensive process, for instance, but it's something to strive towards and something we'll want, but it's got to be a site-specific thing, and dewatering technologies is a whole new area to look at, but it's an interesting topic we should do our next workshop on maybe. But, know your thoughts are on that, Jane.
Yeah. With projects in Europe, one of the big things, land acquisition, land access is a big challenge, and the dewatering is also, it's just impossible to get land big enough for a slurry disposal. So because the dewatered facility is so much smaller, that's another factor driving the use of it.
Yeah, there are a lot of benefits, but in some jurisdictions they're moving towards enforcing filtered tailings facilities for all their operations, which I'd be interested to see how that works out. It's quite a drastic move. So anyway. Okay. Oh, no question yet.
Could you please tell the difference in cost between wet tailings and dry stacking in general, if you can? I know it's site-specific, but...
In general, if you're pumping tailings to your facility, some of the guys here might argue with this, but you're probably looking at 15 cents a tonne to pump tailings to a facility. But if you were to dewater that first, the cost could go up by 10 times to $1, between $1 and $1.25 a tonne or something like that. So that's the kind of impact you're going to have on your operation. The dewatered tailings can't be pumped anymore, so you convey it or truck it. But when you get to the other end, it simplifies things and saves you a lot of headaches. You don't have any excess water in the tailings anymore, so it can be placed and compacted like a stockpile. If you're going for in-pit disposal, you can progressively build up your pit from the base, and if the tailings are acid generating, for instance, you can line the facility as you're going up whilst you're placing tailings in there, and actually achieve both aims. Lining a pit is very fiendishly difficult to do, but rather than doing it as all at once and pumping in slurry, you've got a stockpile there that you can potentially manage. Other benefits are, again, people are asking about in-pit disposal. If you don't have excess water to deal with, you'll get a much higher density in the pit. So you could store 20–30% more tailings in the pit if you keep the water in the plant, as it were, and it saves you having to put in active dewatering in the pit itself to dewater the tailings there. So, yeah, and in seismic regions like this, if you remove that excess water, that liquefaction risk, which I was discussing in detail at San Marco, which led to so many issues, is eliminated because there's no excess water to manage. So you've essentially got a dry mass of material that you can work through. So on low throughput operations, potentially like gold, for instance, it's frequently becoming, all of the scoping studies we're doing, for instance, it's always got to be on the table and it's always looked at. It may be not cost effective, but the benefits significantly outweigh the costs. On the larger, even the larger throughput operations, iron ore, copper, you're looking at 13 million tonnes per annum throughput, something like that. People are looking at that as their base case, and it's going to cost the operation a lot, but if it's economically viable to do it, their permitting will be much, much easier. So that's the other side, which Jane knows a lot more about than me. The permitting side becomes so much more straightforward. As we know, I wouldn't give an example, but up in Romania at the moment, the government is actually moving towards saying that we're not happy permitting things unless you've considered all these dewatering options in a lot of detail and shown us why you can't filter the tailings and why that's not a prerequisite. So it's all scoping studies at the earliest stage, and moving on through the design phases really should be considering all the dewatering options. But we've got paste in the middle as well, we've got thickened tailings. All these things help keep water in the plant and away from the facility.
One more question. Could you please tell some examples which operations are actually doing dry stacking?
Yes, Greens Creek in Alaska is a good example. The climate's probably pretty wet, like Macedonia. It's pretty wet here in Macedonia, not as bad as Scotland, where I come from. It was today, yes. It was pouring with rain outside when we started to talk. so Greens Creek in Alaska does that. It's a gold operation, and the tricky thing there is managing moisture content during placement of material. That's really tough to do, but they do it there. There are a few operations in South America and wet climates in Mexico. I can't recall the names offhand, but it is possible in tropical environments. Where it works really well is in dry, arid climates, because you keep your water in the plant and you stop that. It's a waste to send water out of the facility. So Carrara is the big operation in West Australia, which I understand might be going through some financial difficulty, not because of the tailings facility, but that's the biggest filtered tailings facility in the world. And that throughput's about 12 million tonnes per annum. And our guys in the Perth office designed that facility, and it was a stacker conveyor system. Tailings come out on a conveyor and it's progressively stacked up. So your operational costs are actually quite low. You don't need to continuously rework this material, you don't need to compact it all. But as long as you manage surface runoff off that facility, it's possible. So Carrara is the biggest, certainly the biggest. And Greens Creek in Alaska is another good case study to look at. They're both very well documented. In the EU, planning application has just gone in Northern Ireland at the Carnot project, and they're hoping to use dry stacking in Northern Ireland. Again, the Emerald Isle, green, kind of quintessential Irish landscape. They don't want to disrupt that with a tailings facility. So what they're going to do is create a landform which mimics the natural topography. And you can do all these neat things with land use consultants. You can get visual impact and create swales and drainage features which mimic the natural topography. So they put a lot of work in at that operation to hide the facility, if you like, and that's how they're going to construct it there. So that's at design phase, but that's currently undergoing planning permission. So let's see what the authorities say and if they approve it or not. So there are probably 40 to 50 dry stack operations worldwide now. And the thickened tailings, so tailings at 50–60% solids content, which is still pumpable, is by far the most used method for tailings deposition. But filtered tailings is rising rapidly because it's the future, really. So, yeah. Yes. Anyone else? Everyone's desperate for a beer now, I think. So. Well, thanks very much, everyone, for your time, and please contact any of us if you have any more questions.